Hello and welcome. This is part 1 of the two-part lesson on post-processing of CFD simulation results of an FSAE car. In the previous lesson, we discussed how to set up the solver and monitor conversions of the CFD simulation of the FSAE car using Ansys Fluent. In this lesson, the focus is on understanding the physics of the airflow around the car using various post-processing techniques for extracting the data from the simulation results and visualizing it using tools available in Ansys Fluent. In this part specifically, we will first calculate the drag force and lift force experienced by various parts of the car and the car as a whole. Then, we will study the flow characteristics by plotting the contours of pressure, velocity and static pressure and look at the vectors and scenes. Excited? Let's get started. Before going further in the lesson, if you want to learn the basics of post-processing and how to use common post-processing options, please visit the Getting Started with Fluent Basics learning track, whose link is included in the lesson page. Launch Ansys Fluent in solution mode. Load the provided case and data files of the simulation that we have saved after the completion of the solution in the previous lesson. Now let's focus directly on post-processing of the results. There are various options available under the Results tab to analyze different elements during post-processing. Surface Group helps us to create several types of additional surfaces which are helpful in visualizing and reporting values on those particular surfaces. Using the Graphics Group, we can create contours, vector plots, path lines, etc. for qualitative post-processing. We can also obtain and plot numerical results such as fluxes and forces using Plots and Reports group. Now, let us understand how to extract the lift and drag forces experienced by the different car components. Click on Forces under the Reports group. Select all the wall zones related to the FSAE car as shown. Make sure that the option is set to Forces and the direction vector value for x is set to 1, which is the flow direction, to obtain the drag force values. Hit Print button to display the values in the console. In the console, you can see the drag force values and the corresponding drag coefficient for various parts of the Formula SAE car as well as the drag force experienced by the whole car. Both drag force value and drag force coefficient are divided into two parts, namely pressure and viscous. Pressure force is the net normal force acting on the component which leads to the pressure drag part of the total drag, and viscous force is the net tangential force on the component which leads to the skin friction drag part of the total drag force. As can be seen from the values, chassis, front wing, side wing and rear wing are the major contributors of the drag force. Similarly, to estimate the lift force, change the direction vector by entering 1 for y, that is flow normal direction or upward direction, and 0 for others as shown here, and hit print. The net lift force is negative, which indicates that the net force being experienced by the car is in the downward direction, which is generally referred to as the downforce. Not all components of the car produce downforce, specifically the tires. It is the job of the engineer to ensure that there is a net downward force produced by the car so that it can stick to the ground at all times. For a higher speed series like Formula 1, downforce plays an extremely key role in enabling the car to achieve high cornering speeds. As you can see here, all the wings, chassis and the diffuser are major contributors for generating downforce. Now, we will see how to use different contours and vectors to visualize the airflow around the car. Before doing that, let's display the entire car geometry. Click on the Display Mesh button and select parts related to the FSAE car as shown. we can see only half of the car in the window as only half a portion of the car was simulated. To display the entire car for post-processing purposes, select Views option from the View tab. Once the Views dialog box is displayed on the screen, check the Symmetry zone under Mirror Planes and click Apply. Now let's have a look at the velocity distribution around the car. Click on New under Contours in the Graphics section. First, we will plot velocity magnitude plot on the symmetry plane. Change the contour name to Velocity Magnitude Symmetry and change the settings as shown. Make sure that Global Range option is unchecked before hitting the Compute button. This restricts the max and the min values of the plotted contour to those on the plotting surface, which is symmetry plane in this case, instead of the entire domain. Click on Save/Display button to visualize the contour plot. You can move, pan and zoom around with the contour as needed. Here we can observe low velocity and high velocity regions represented by blue and red color respectively. Looking closely, you can observe that the air is accelerated to higher velocities under the car. This is due to the conservation of mass. As air hits the car, it must go around and some of it squeezes under the car. According to Bernoulli's principle, this leads to the acceleration of the airflow and subsequently to the creation of a low pressure region beneath the car when compared to above it, leading to the generation of a net downward force we call downforce. This can be verified by plotting XY plot of static pressure on the line passing through the bottom of the car. For that, let's go to Surface Group and draw a line. We will be drawing the line which goes under the car, starting at the front of the car to the rear end of the car. Enter the coordinates as shown to create the line. Next, go to the Plot group and create a new XY plot. For Y-axis function, select static pressure. In the surface, select the recently created line and plot the XY plot. Here is the generated graph. For better understanding, we have overlaid the car on this graph with proper scaling. Here, the first dip in pressure is due to the presence of the front wing. Next, due to the shape of the underbody under the nose cone, we observe the second dip. To understand the third dip, let's look at the physics of the airflow. The flow from below the car needs to exit and re-merge with the surrounding ambient pressure, which is facilitated by a device called the diffuser. Owing to its diverging shape, with the inlet area less than the outlet area, due to Bernoulli's principles, a further acceleration of the airflow occurs, leading to a third dip in the pressure around the location of the diffuser inlet, resulting in an increased downward force than when compared to the vehicles without a diffuser. Beyond the diffuser, the static pressure of the air rises steadily and becomes equal to the ambient pressure. Here is the equivalent pressure contour on the same plane. This further corroborates our observations from the velocity contour and the static pressure plot. Now, let's look at the pressure contour on the surface of the car. Before that, let's make the mesh color uniform, which will be helpful while reading the contours. This can be done by using Colors option in Mesh display. Click on Colors, then select By Type under Options, select Wall Surfaces and set the color to white as shown here. Open a new contour from the Graphics group of the Results tab and rename it as Contour Static Pressure. Select all the surfaces related to the car only as displayed on the screen. Uncheck the Global Range and, if required, check the Contour Lines and Draw Mesh options. This will help the user to display and read the pressure distribution over the car surface more discreetly. Make sure the contour is set to Pressure Contour and Static Pressure before clicking Compute. In the Pressure Contour dialog box, after clicking on Compute, minimum and maximum pressure values are displayed. To plot the pressure distribution, click Save/Display. Click on the negative x-axis here to display the car from the front view. Here you can observe the high pressure surfaces, and if you view the car from the back, you will observe the low pressure surfaces. This pressure difference is what contributes to the pressure drag part of the overall drag force. To view the pressure points more distinctively, uncheck the auto range option and set the pressure settings as shown. Change the minimum and maximum values to -170 and 170 Pascal respectively to plot the pressure gradients on the car surfaces. Check Draw Mesh option and click on Save/Display. As can be seen in the graphics display, high pressure and low pressure regions are present on either side of the aero devices such as front wing, side wing, rear wing, as well as on the tire surfaces and the driver cockpit region. This difference in pressure, depending on the net direction, contributes to the downforce or drag generated by the component. Now, we will look at the airflow around the car using velocity vectors. Velocity vector plots, also known as velocity vector field plots, are graphic representations of the velocity field in a fluid domain. To plot velocity vector on different planes, first we need to create reference planes. Open the plane surface dialog box as shown and select XY plane under the method dropdown. Enter the Z value as -0.68 meters and rename the surface as Z equal to -0.68 and hit create. Now click on new here to create a new vector. Rename it velocity vector on plane. Select Z equal to -0.68 from the surfaces and check the Draw Mesh option. Select the appropriate options and put the preferred values for scale and skip, and then click on Save/Display. Since we have mirrored the car in the beginning of this lesson to show the full car, the display also shows the mirrored vector contour on a plane in addition to the original vector contour on the selected plane. We can now visualize the fluid flow behavior around the car. Because of the rotational motion of the wheels, we see that the airflow near the wheels also has a strong rotational component. We also observe flow separation and recirculation regions behind the front wing and the tires. Now let's look at the scenes. Sometimes it may be possible that you want to view more than one post-processing elements together to get more information about the flow. This can be achieved through scenes. Let's plot the scene for different contours and vectors. This scene will help us to understand the velocity distribution around the car. Create a new mesh for the scenes as shown, then right-click Scenes in the outline view to create a new scene for viewing multiple contours at once. Choose the appropriate contours from the list. In our case, let's select Mesh 1, Velocity Vector on Plane and Contour Static Pressure from the list. Adjust the Mesh 1 transparency to 70% and click Save and Display. By observing the scene, one can compare selected plots and study the similarities and the dissimilarities between them. This is very helpful to predict the flow nature around different parts of the car. Similarly, we can plot different scenes as shown here. Let's summarize what we have learned so far. In this part 1 lesson, we focused on a certain method to analyze the results from a CFD simulation of an FSAE car. We started the lesson by discussing how to extract both component specific and the overall drag force and the downforce values. Then we learned about the effect of flow interactions with the car surface on velocity and pressure of the fluid. Using velocity contour and the XY plot of static pressure on a line, we saw the effect of underbody and the diffuser on the flow beneath the car. Next, using velocity vectors, we learned how to look at the general fluid flow around the car and specifically focused on the rotating flow near the wheel. Finally, using scenes, we learned how to display multiple post-processing elements together for better interpretation of the results. This brings us to the end of the lesson.